Hi guys, welcome to the video for chapter 5.4.2 where we are looking at electromagnetic fields. So let's jump right into this. We have 3 learning objectives today. So our first learning objective is to describe the direction of magnetic field lines around a wire carrying a current. Now current, you'll notice I put that in red. This is standing for what we normally call conventional current. But current and conventional current, we sort of use that interchangeably in physics. And then the what we would normally call regular current, they like to call that electron flow. So you'll actually see the word electron for electron flow. Sorry, my iPad is standing up straight, so my writing is not as nice as it normally is. So what we need here, what we've got here first off is I want to outline an extra little bit of notation that we're going to be using. So normally we have our 4 directions. We have up, down, left, and right. And so what we're also adding into this is a 3-dimensional notation of an object going into the paper or coming out of the page or the paper. Now, the quick way to imagine this is either an arrow or maybe a dart. So a dart usually looks something like that, where there's a cross at the back of it. So if the dart is going away from you, you can see the cross at the back of the dart or the arrow. And when the dart or the arrow is hitting you, it's going to be the tip that hits you first. And so that's why when it's coming out of the page towards you, essentially, it is the dot notation right over here, okay? And if it's going away from you, it is the cross, okay? So the first activity is I want you to, by the way, sorry, I forgot to mention, you'll probably want to have an empty transparent water bottle for today's lesson and also a pen or a pencil. And so what I'm going to do is I'm going to actually go over to my camera now, whoops, and I'm going to explain to you the right hand rule. So here, this is my right hand. And so you want to try this out yourself, okay? So your thumb is now pointing in the direction of conventional current, okay? So the positive charges are flowing in this direction. So your pen would probably represent maybe like a wire or something like that. So I suppose you could actually use it like a wire like this, okay? And so if you had a longer wire, this is now pointing in the direction of positive charges flowing this way, okay? So naturally, the electrons would be flowing in the opposite direction, going this way. But we usually don't talk about electrons flowing around. Now, your 4 fingers, so I'm going to just use my pen here, or pencil, and these 4 fingers that wrap around, I'm just going to try to show you here, they're going to circle around the wire, essentially, okay? And so it forms a circle, okay? So you could call it a clockwise or an anti-clockwise circle, but you could also think of it as different directions. So on top of the pen or the pencil, so this is the direction, right? These fingers are now pointing, I guess, towards you, towards the camera. And as it wraps around, now it's pointing down. And then at the bottom, it is now pointing away from the camera or away from you, okay? And then on the back side, okay, so I'm going to try to twist my body, okay? So thumb's pointing that way, my right hand, right? These 4 fingers are now pointing up when it's behind it, okay? So that's what the right hand rule is about, okay? So remember, thumb represents conventional current or positive charges. These 4 fingers that circle around represent the magnetic field. Okay, so that's what I was trying to illustrate here in this diagram. And the fingers actually point towards the north, okay? So the north is actually always changing. And we're going to look at some diagrams to show that and illustrate that. So you can see that the North Pole, depending on where you look at it, it forms sort of a tangent from that, okay? So it forms a tangent, and that's where the north points at this particular moment, okay? If we form another tangent here, okay, that's where north points at this particular moment, okay? And then here, okay, so it always sort of right on the tangent, that's where the North Pole is going to be pointing towards, okay? And your fingers point towards that particular direction. So 2 different illustrations that you can observe here. Current coming out of the page on the right-hand side, okay? And then the magnetic field is circling around, okay? Around that. Okay, second learning objective, describe the shape and spacing of the magnetic field lines around a wire carrying a current. So this is very similar to what we've already talked about in the past, is the magnetic field strength is larger closer to the wire because there's a greater density. So not just because, I mean, diagrammatically we can see that there's a greater density, but there's other things to do with that, okay? But for now, just know that if you see a greater density of lines, that is going to be a stronger magnetic field or larger magnetic field, and this is going to be a weaker magnetic field. So I'm going to use the word weak. I probably should have written strong instead of large, okay? But a larger magnetic field strength. Okay, so strong rather than large. Take your pick, large or small, okay? So that's the shape of the magnetic field lines. It is going to form a perfect circle for a wire, but we'll look at solenoids in just a moment, okay? So first example here is, you can try this out for yourself. So you might want to pause the video. You can read the question. Given the magnetic field line shown near a current carrying wire, identify the current direction. So go ahead and pause the video, and you can write this down or just kind of do this exercise mentally. So we have option A and B here. Okay, so hopefully you've kind of thought about that. For option A, this is coming directly out towards you. So I'm going to use red just to indicate conventional current, okay? So you can use the right hand rule. The thumb is going to be pointing towards yourself, okay? And then your fingers, your other four fingers would curl up. In diagram B, the wire would be the current, conventional current, positive charges going to the right. So point your thumb to the right, okay? And if you have your pencil pointing to the right, your fingers are going to come out on top of it. So your fingers are going to come out on top towards you. Oh, this is really, really difficult. And then these fingers are going to point away from you into the actual page itself, okay? So that's example number 1. All right, third learning objective, describe the magnetic field lines outside and inside a solenoid using the right hand. Okay, so this is where you're going to want to have a water bottle. So a solenoid is essentially an object with a bunch of wires wrapped around it. We'll see some diagrams in just a moment. But what we're actually seeing here in this diagram is we're looking at 2 wires with the current going in the same direction. So probably should have used red for that. So the current is going in the same direction into the page. And you can see very close to the wires, like directly beside the wires, the magnetic field lines are separated. But further out, the magnetic field lines are actually joined together. Okay? So that actually strengthens the magnetic field. So here you can see 2 different diagrams. This is the same as the diagram above, where the current in the wire is in the same direction, and you have a strengthening of the magnetic field. Over here on the right-hand side, I'm just going to label this as A and B. So for B, the current is going in opposite directions, so you don't have a strengthening of the magnetic field, as you can see in the diagram there. Okay, so this is the solenoid that we're trying to talk about here. So again, I'm going to just go over to my camera here, and I have to flip that around again. So here we have a bottle. So this is where it's really, really helpful. Use your right hand, okay? And essentially your fingers, I mean, if you actually do have a wire, this is actually kind of helpful. So you can kind of wrap, I wish I had a longer wire. So your thumb points into the wire, okay? So follow along with your wire. So now my finger's actually behind this, right? Okay, and then my fingers can actually go, it would also be helpful if I had a bigger bottle, but I'm just going to use 3 fingers here, okay? So the 3 fingers point into the bottle, okay? And the thumb always circles around that, okay? So it doesn't matter where the bottle is, okay? But as long as you follow the first wire, you can wrap it around a few times. And so I'm just using a shorter wire here, and it'll wrap around, okay? Your fingers then point inside, okay? Same thing, the thumb represents the direction of conventional current, so positive charges flowing through the wire, goes like this. These fingers now point in the direction of the magnetic field. So specifically, they point northwards. So actually, what actually happens is, if this points north, so if you can slide your fingers all the way through, this end of the solenoid is going to be the north end, and this side where it started is going to be the south end. All right, so let's go back over here to our diagram. So that's what we're seeing here is, so for this particular diagram, your hand is probably a little bit awkward. If you need to point your thumb down this way, okay, and then your four fingers are going to point in that particular direction, okay, which is north, okay? So at one end of the bottle is going to be the south end where your fingers are entering the bottle, and on the other end, probably the sealed end, the base of the bottle, is going to be the north side, okay? And your thumb is probably going to be pointing downwards like that, okay? All right, let's look at a few other diagrams here. So just to give you guys some other ideas of seeing that, okay? So just follow the wire direction with your thumb, okay? And your fingers always point in the direction, no matter how you curl it as the magnetic field. Here we have another example here. So you can, again, sort of imagine the water bottle here. So here's the water bottle, okay? And then you can slide your fingers into that, okay? And then so this would be the south side, and this would be the north side, okay? Is how that would work. Here, this is a really clear diagram of the current that are all glued together, okay? So actually, I'm just going to go back over here. So if you imagine the positive charges coming through this guy, right? At this particular point down here, it is going into the page. It's going to travel up, then it's going to come out of the page, and then it's going to circle back down, sort of a loop-de-loop, okay? And here it's going into the page again, up behind it, out of the page, okay? And so that's why when you look at the other diagram down here, it's always consistent, okay? When you start wrapping the wire around, what happens is that the current will always flow into the same direction, and that's why you have a strengthening of the magnetic field, okay? So for this second exercise, again, imagine that there's a solenoid that we see here. Current is going up, as you can see, through the red wire here. And then so identify the north and south poles. So go ahead and pause the video and think about the direction for that. Okay, so hopefully you've had the chance to think about that. So the current is going up. And so the best way to think about this is, I'm trying to get my bottle here. So it is kind of up and behind it. I probably should have had it wrapping around in front of it. Probably would have been easier. But it is still going to, your fingers are still going to enter this way. So essentially the south pole is going to be here, and the north pole is going to be on that side, okay? So it's kind of a bit tricky. You might have to get up out of your seat and orient the bottle and maybe like a charging cable around that. Okay, but that is exactly what you're going to get. Okay, guys, that was, I went through that pretty quickly, but it is going to be kind of challenging. So do use some props, use the water bottle, use a wire, wrap it around it just to get a little idea of that, okay? And also use a pencil for that right-hand rule, okay? Remember, your thumb is conventional current, four fingers, magnetic field, pointing northwards. All right, guys, see you next time for 5.4.3. Take care. Bye-bye.